Welcome to this explainer. I'm absolutely thrilled you're here. Whether you're gearing up for an exam or just looking to sharpen that mathematical toolkit of yours, we're going to break down KSSM Form 3 Mathematics, specifically Chapter 2. We've got two incredibly powerful concepts on the docket today: significant figures and standard form. Let's get right into it. But before we do, just think about this for a second. How exactly do mathematicians and scientists measure something as massive as the entire Earth, or, something as microscopic as a single cell, without getting completely lost in an endless sea of zeros? Well, today we're going to uncover the elegant mathematical solution that lets us write, calculate, and really just understand these massive and microscopic numbers with absolute precision. Okay, let's dive into this. Here is our learning journey for today. First, we'll master significant figures. Then, we'll write in standard form. Third, we'll calculate with standard form. After that, we'll actually solve for the Earth's surface area. And finally, wrap up with a chapter summary and some tips. Section 1. Master significant figures. Before we can tackle those giant numbers, we really have to understand the rules of precision. It all comes down to accuracy, right? In math, accuracy is just the degree of approximation of a measurement to its actual real-world value. It shows us the level of precision. Basically, every single digit we write down, especially those trailing decimal zeros, tells us something specific about how exact our measurement truly is. And that's where significant figures come in. They are the specific digits in a number that communicate this exact level of accuracy. So how do we actually count them? Well, there are 5 fundamental rules you need to keep in your back pocket. First off, all non-zero digits are always significant. No exceptions. Second, any zeros sandwiched right between non-zero digits, those count too. Third, zeros at the end of an integer, well, that actually depends on the required level of accuracy. Fourth, zeros at the end of a decimal are always significant because they explicitly determine that decimal's accuracy. And fifth, this is a big one: leading zeros, meaning the zeros before the very first non-zero digit, are never significant. The counting always starts from the very first non-zero digit. Now, what's really interesting here is how the context completely changes a simple integer like 15,000. Let's say our accuracy is only to the nearest 1,000. In that case, this number has just 2 significant figures. But if we measured it to the nearest 100, suddenly it has 3. To the nearest 10, it has 4. And if we measured it perfectly to the nearest 1, all 5 digits become significant figures. So context is literally everything when you're dealing with integers. Let's actually see this in action by rounding the number 63,479 to exactly 2 significant figures. All right, step 1. We find that second significant figure, which in this case is the 3. Step 2, we glance at the digit immediately to its right. That's a 4. Step 3, since 4 is less than 5, our target digit, the 3, just stays exactly as it is, unchanged. Finally, we replace the 4, 7, and 9 with zeros since they sit before the decimal point, so our final perfectly rounded answer is 63,000. Easy, right? Okay, now let's try a decimal. We're going to round 0.008146 to 3 significant figures. Remember that 5th rule we talked about? Leading zeros aren't significant, so we completely skip those zeros and start counting at the 8. 1, 2, 3. Okay, our 3rd significant figure is the 4. Next, look to the right. We see a 6. Now, because 6 is greater than 5, we bump up that 4 by adding 1, making it a 5. And since this is a decimal, we just drop that trailing 6 entirely. We do not replace it with a 0. That gives us a precise answer of 0.00815. Section 2. Write in standard form. Now that we've got our accuracy skills on lock, we are moving on to the ultimate tool for handling extreme numbers. This right here is the golden rule of standard form. For a number to be in proper standard form, it absolutely has to be written as a times 10 to the power of n. And here is the vital condition. A must be a digit between 1 and 9 inclusively, and n has to be an integer. Honestly, just burn this format into your memory. It's that important. Let's watch how a really small decimal like 0.003025 transforms into standard form. We know our a needs to be between 1 and 9, right? So we're going to grab that decimal point and move it right after the first non-zero digit. That gives us 3.025. But to keep the whole mathematical equation perfectly balanced, since we move the decimal point 3 places to make the number larger, we have to multiply it by 10 to the power of -3. And there you have it, a neat, standardized 3.025 times 10 to the power of -3. Section 3. Calculate with standard form. Now for operations. When you're adding or subtracting these formatted numbers, you can't just combine them randomly. So the crucial point here is this. You absolutely must ensure both numbers share the exact same power of 10 before you do anything else. If they don't match up, you have to manipulate the index of one of them until they do. Once those powers of 10 are identical, you just extract that common power and add or subtract the decimal values in the parentheses. But for multiplication and division, we actually rely on a totally different set of rules, the laws of indices. Think of these as your secret weapons. When you're multiplying standard form numbers, you multiply the base decimals and then you just add the indices together. So m plus n. When dividing, you divide the base numbers and subtract the indices, m minus n. Let's slowly unroll one of these calculations step by step so you can see it in action. We are solving 3 times 10 to the power of 5 multiplied by 4.9 times 10 squared. First up, we group those base numbers together. So 3 times 4.9 gives us 14.7. Next, we tap into those laws of indices and add our powers. 5 plus 2 is 7. Okay, so now we've got 14.7 times 10 to the power of 7. But wait, look closely at step 3. 14.7 totally violates our golden rule, doesn't it? It is not between 1 and 9. So we have to adjust it. We convert 14.7 into 1.47 times 10 to the power of 1. Finally, we just combine all those indices, 1 plus 7, to get our perfectly formatted final answer, 1.47 times 10 to the power of 8. Section 4. Solve Earth's surface area. Let's bring all these skills together for a massive real-world application. We are going to calculate the surface area of the Earth, and we need to give our answer in standard form, correct to 4 significant figures. First things first, we need the radius. Our source tells us the diameter of the Earth is 1.2742 times 10 to the power of 4 kilometers. We just divide that by 2, which gives us a radius of 6.371 times 10 cubed kilometers. Now we plug that straight into our surface area formula, which is 4 times pi times the radius squared, and we'll go ahead and use 3.142 for pat. Now, when we actually do the math, multiplying 4 by 3.142 by r squared radius, our calculator is going to spit out this absolute monster of a number. Look at this, 510,130,608.1 kilometers squared. I mean, this chaotic, unrounded number is exactly why standard form was invented in the first place. It's way too long, it's incredibly prone to being misread, and honestly, it implies a level of exact accuracy that we just don't actually have. And this brilliantly illustrates the power of what we've learned today. Remember, the original question asked for exactly 4 significant figures. So we take this giant number, locate the 4th significant digit, which is that 1, we look to the right at the 3, and we leave the 1 unchanged since 3 is less than 5. Then we apply our standard form rule, moving that decimal point 8 spaces to the left. Instantly, we compress that massive, messy number into something incredibly elegant and readable, 5.101 times 10 to the power of 8 kilometers squared. Simple, precise, and honestly, pretty beautiful. Section 5. Chapter Summary and Tips. Let's wrap this up with a quick review to lock in all this learning for your exams. Here are the core takeaways and the most common pitfalls you want to avoid. First, whenever you add or subtract standard form numbers, always double check that you've manipulated them to have the exact same base power of 10. Second, check your final answers. Make sure your A value is strictly between 1 and 9 inclusively. If you end up with a 14.7 like we did earlier, you've got to convert it. And lastly, never forget those rounding rules, especially the crucial difference between dropping trailing decimals and replacing integer places with zeros. We've seen firsthand today how standard form and significant figures can easily tame and capture the incredibly vast surface area of our Earth. So I'll leave you with this thought. With these mathematical tools now firmly at your disposal, what impossibly small or massively huge parts of the universe will you measure next? Thanks so much for hanging out with me in this explainer, and keep exploring.